electric potential as well as relation between electric potential energy and electric force in this video. In assembling the system where the charges were originally at infinity without any change in the kinetic energy of the charges. So the important point to know is that the potential energy is defined in terms of work done by an external force. The potential energy of a system of 2-point charges is equal to Q1, Q2 divided by 4 pi epsilon 0 R. Note that this equation is only valid for 2-point charges. What is the potential energy of a system of more than 2-point charges? In this case, we will bring one charge from infinity to a particular point. In this case, there is no work done because there's no force acting on this charge. Next, step 2, we bring Q2 from infinity to the point. As Q1 is already in place, it will have to set up the electric field in the region, and an external force will need to do work against the electric force experienced by Q2. So the work done is Q1, Q2 over 4 pi epsilon 0 R12. Okay, step 3, we are going to bring Q3 from infinity to its point in the electric field. Since Q1 and Q2 are now in place, the electric field in the region is now due to Q1 and Q2. The external force would need to do work against the force on Q3 due to its interaction with the field set up by both Q1 and Q2. So work done by W3 will be Q1, Q3 divided by 4 pi epsilon 0 R13 plus Q2, Q3 divided by 4 pi epsilon 0 R23. So the potential energy of the system will be W1 plus W2 plus W3. So it's a scalar addition, or we call that arithmetic addition. Electric potential. The electric potential at the point in the electric field is the work done per unit positive charge by an external force in bringing a small test charge from infinity to that point without any change in kinetic energy. So V is equal to W over Q, where V is the electric potential, the units is the volt or joules per coulomb. The electric potential in the field of a point charge Q is given by 1 over 4 pi epsilon 0 Q divided by R. Okay, note that this equation is only valid for point charges. If I have 2 or more point charges, how do I determine the potential at a point in the electric field set up by these point charges? So since the electric potential is a scalar quantity, the potential at the point in such electric field is a scalar sum of the potential contributed by each charge at the point. So example 4, 4 charges are placed at the corners of a square. Each side has a length A. Find the resultant electric potential at P, the center of the square. So using Pythagoras theorem, the distance between the corner of a square to P is given by A over square root 2. Okay, the working is below. Electric potential at the center of the square is given by 1 over 4 pi epsilon 0, 1 over A square root 2, which is a distance from the corner to the center. And then you look at the contribution from each charge. So there are 4 charges, Q, 2Q, another 2Q, and then a minus 2Q. So moving between 2 points in electric field, the change in potential energy in moving a charge Q from point A to point B in the electric field is given by delta U equal to UB minus UA. And UB is QVB and UA is QVA. In physics, change means final minus initial. And note that this equation is valid for all cases. Okay, note that the change in potential energy is the work done by the external agent in moving Q from A to B. Example 5, an electron in the vacuum of a cathode ray tube moves from rest at the point where the potential is minus 1400 volts to a point where the potential is 0. Calculate the change in potential energy. The change in is minus 2.24 times 10 to the power minus 16 joules. The symbol used is used for potential energy in this case. It is also used for internal energy for thermal physics. So for example, for an ideal gas, microscopic PE is 0, so internal energy equals to microscopic kinetic energy. Hence, for the ideal gas, U represents the kinetic energy. Conservation of energy means that the final total energy equal to the initial total energy. From there, we can get delta KE equal to minus delta U for this case. Since the energy is conserved, delta K equal to minus U, and we get change in KE as 2.24 times 10 to the power of minus 16 joules. So we get velocity as 2.22 times 10 to the power 7 meter per second. Relation between electric potential energy and electric force, F equal to minus du dr. This is an important equation. Can recall that the potential energy is the work done by an external force to bring a charge from infinity to point R. So work done is given by the area under the force displacement graph. The work done by the external force increases the potential energy of the system. That is why we define potential energy in terms of work done by an external force. Mathematically, area under the graph is given by the integral Ku is equal to W. W is the work done by external force. So it's the integral of F external dr. So we know that the electric force and the external force are opposite in direction. And for vector quantity, it is represented by a minus sign. So U will be equal to minus F integral of F dr. The differential form of this equation is F equal to minus du dr. Okay, in words, we say that the magnitude of the force is equal to the potential energy gradient. The direction of the force is opposite to the direction of increasing potential energy. Okay, consider point 2 in terms of gravitation. Okay, gravity points downwards. The direction of increasing gravitational potential energy is upwards. In other words, the potential energy increases as the height increases. Hence, we say that the direction of gravitational force is opposite to the direction of increasing potential energy. Okay, note that this equation gives us both the magnitude and direction of the force acting on the charge placed at the point in an electric field. The magnitude of the force is given by the value of the du dr, and the direction of the force on the charge is given by the negative sign. So the force on the charge points in the direction of decrease in potential energy, or we can say opposite to the direction of increasing potential energy. Relation between potential gradient and electric field strength. Since F equal to minus du dr and F is QE and U is QV, we get E is equal to minus dV dr. So dV dr is known as the potential gradient of the field. Okay, this is a technical term, please remember. Du dr is known as the potential energy gradient of the field. Okay, some comments. Okay, E is equal to minus dV dr. So we can change to the integral form. Integrate E dr equal to minus integrate dV. So integrate dV will give you delta V. So delta V is equal to minus integral of E dr. So from equation 1, the gradient of VR graph gives the magnitude of the electric field strength E. From equation 2, the area under ER graph gives the negative change in potential. So questions based on information from VR and ER graphs are common for A-level. Graphs of electric field strength and electric potential between point charges. An isolated conducting sphere of radius r is given a charge of plus q. This charge may be assumed to act as a point charge situated at the center of the sphere, as shown in figure 5.1 and 5.2, as shown in figure 5.1. Figure 5.2 shows the variation with distance x from the center of the sphere of the potential V due to charge q. State the relation between electric field and potential. So given the E equal to minus dV dr, the magnitude of the electric field strength at a point in the electric field is the rate of change of the electric potential with respect to distance, or we say it's the potential gradient. The negative sign indicates the electric field always acts in the direction of decreasing electric potential. So B, using the relation in A, sketch a graph to show the variation with distance x of the electric field due to the charge plus q. Inside the sphere, the electric field is 0, and outside, the electric field follows 1 over r squared. The extension for example 6. An isolated conducting sphere of radius r is given a charge of plus q. So the VR graph or Vx graph follows q over 4 pi epsilon 0 r. So which means that V is proportional to 1 over r. But for the electric field strength is positive when R is positive, when X is positive, but it's negative when X is negative. Why is V positive for negative X, but E is negative for negative X? So let's look at the conducting sphere again. So E points to the right, so E is negative. E points to the right, so E is positive. On the left side of the sphere, E points to the left, so E is negative. So E is a vector, and the positive and negative signs represent directions. It is positive to the right of the sphere because E is pointing to the right. It is negative to the left of the sphere because it is pointing to the left. V is a scalar, and the positive and negative signs represent magnitude. So the magnitude of V is positive everywhere because the charge is positive. Okay, example 7. Sphere A and sphere B are charged conducting spheres of radius r with charge QA and QB respectively. Okay, sketch the graph of electric field strength against R and electric potential against R. Okay, for case A, both spheres are positively charged. Okay, the magnitude of A is double the magnitude of charge B. So this is what the electric field look like. Okay, E is proportional to 1 over R square. For charge B, QB is negative because the electric field vector is pointing to the left. Now in this case, for potential, it's a positive charge for both of them. So the potential is positive for QA and QB. So in terms of the resultant electric field, E will be the sum of QA and sum of QB. So it's represented by the red line. And for the potential, is also the sum of VQA and VQB. Now note that at the point when the electric field is 0, the value of the potential is at the minimum. So dV dr equals 0, that means it's a minimum point. Okay, next we look at A is positively charged and B is negatively charged. So in this case, the electric field line looks like this. EA is positive because the electric field is pointing to the right. Now EB is also pointing to the right because QB is negative. Now for the potential, VA is positive because charge QA is positive. VB is negative because charge VB is negative. So the resultant will look like this for the electric field and looks like this for the potential. We have come to the end of section 12.3 and section 12.4.